Alright, welcome back to the drive-thru, boys and girls. Hope everyone's having a wonderful Monday. Got a case of the Mondays? Stop by the deli. Get yourself a three-way. Nothing cures the case of the Mondays like a fresh three-way from the deli. And some snacks, some veggie straws. Alright, so this is 12.6. It's our first section in our second sub-chapter of Chapter 12. And we're first going to introduce you the gradient vector. Okay, so if a function is of x of y, then the gradient of f, which is sometimes referred to as del f, okay? The gradient of f is f sub x, the partial derivative with respect to x, is going to be now a component of our vector, okay? And the partial derivative with respect to y will be the j component of our. So the gradient, in this case, kind of seems pointless, okay? We're just attaching a function that is the derivative with respect to x to one aspect of a vector, and we're attaching a function that is the derivative with respect to y for the other aspect of the vector. So just stay with me and trust me that this will actually end up being very useful. Let's just figure out how to find it. So let's just practice. Del f is equal to, no, it's del. It's del. It's like an upside down delta that's been stretched. Is it no? No. It's the gradient. Alright, so the gradient would be the partial. What's the derivative of the natural law of x? Alright, so this would be y over x, right? Plus y squared. Did I get the partial derivative with respect to x right? Okay, and then plus ln of x, oh, ln, I get it now, plus, no, 2xy in the j direction, right? Okay, now, there's something I want you to know about this question. This is the way the question is posed in the book. But this is actually a little bit misleading, okay? Because what would you consider this function? Would you consider it to be a surface? Yes, it is. It has a z value. This is the misleading part. Okay, so I'm not going to sketch this surface because I can't and I don't feel like it. Okay, but let me just sketch a surface. Okay, let's say this was our surface. And then when we put in the point 1, 2, natural log of 1 is 0, right? So you get 2 times 0 is 0. Plus 1 times 4 is 4. When you put in the point 1, 2, you get a 4. So what they're really asking you is find the gradient at the point 1, 2, 4. But you're not going to plug in that 4 at all. So they're actually trying to save you from making a mistake, but in doing that, I think they kind of confuse you. Does that make sense? Okay. So, now, to find the gradient, we're going to put 1 and 2 in for these values. So then we're going to end up getting a, let's see, y over x is 2, plus 2 squared is 4. So that's a 6, right? Did I do that right? 6. And then you get a natural log of x is 0, plus 2 times 2 is, so you get 6, 4 is our del f of 1, 2, or the gradient at 1, 2. Okay, now, later on in this video, this will make more sense to you. So for now, I just want you to look, pay attention. Okay, what that tells us is that at the point 1, 2, so imagine this, like it's a shadow right there, and this red point is directly underneath the black point. Okay? At that point, our gradient is forward 6, right 4, so it's something that looks like this. This is the geometric representation of the gradient of f. Okay? Can you remember that? At this point, you should be totally confused and wondering what in the heck that's telling us. So if you feel that way, excellent. You're doing great. All right? Next. That is my map of Winton Woods, drawn with a mouse. If you've ever been to Winton Woods, this is pretty good. This is Winton Road. This is the walking trail. The blue line's the lake. I just was explaining to some girl in my study hall where she could go take a good hike, which is right there. But it has nothing to do with our lesson. I forgot I interrupted it. Next. All right. Directional derivatives. Okay? So in the first 5 sections of this chapter, we learned how to find the partial derivative with respect to x and the partial derivative with respect to y. And that was useful for related rates, which is very useful. But we also acted like it was useful because we could find the change in the direction of the xz plane or the change in the direction of the yz plane. Do you remember that? Well, now with our gradients, we can actually find our change in any direction that we want, which is way more useful. Okay, we are so much more empowered by this. So, to find the direction vector, first of all, that is this. Those are notations for our direction vector. What direction do you ask? Whichever direction you want. Literally whichever one you want. Okay? So, to find our direction vector, d sub u, you take the partial derivative with respect to x and the partial derivative with respect to y, or you just take your gradient function and dot it with u, where u is a unit vector in the desired direction. Okay? Now, hopefully you remember that unit vectors have a magnitude of 1, so that another way you can find them, because sine squared plus cosine squared equals 1, hopefully you remember that this is another way of representing a unit vector. Okay, so these red boxes that are double boxed, those are your 2 methods for finding the directional derivative. The easiest thing you can do is dot it with a unit vector. Dot the gradient function, or the gradient operator. That's what you call it. It's not a function, it's an operator, I guess. Okay? So far so good? All right, let's practice that. So, find the directional derivative of, okay, so we got our function of multivariables. So I know that we're going to need to find our f sub x. So what is that? 6x, right? And s sub y is a negative 4y. And we're going to need to find pq. So it's q minus p. So that's 0 minus a negative 3/4, which is a positive 3/4. And 1 minus 0, which is 1. Is that a unit vector? It is not. So we need to find the magnitude of PQ, which is the square root of 9/16 plus 16/16, and that is the square root of 25/16, which is 5/4. Okay? So to find the unit vector in the direction of PQ, U is our vector PQ divided by its magnitude, which ends up being 3/5, 1/5. Is that right? No, 3/5, 4/5. Sorry. Okay? Got it? So, our gradient is well, it's this. 6x, negative 4y dot 3/5, 4/5. All right, quick cumulative review question. Dot products. What's my result? It's a scalar. That's good, because what's the gradient? What's the directional derivative telling us? It's telling us the slope of the line in the plane that's defined in the direction that we want. Does that make sense? Okay. So you get 18x over 5 plus a negative 16y over 5, and we know that our x is, no, we got to put this point in. Okay? Oh, does that multiply out to be 0, Ted? 18 times negative 3, negative 54 over 20. I'm just going to write that down. Right? Did I do that right? Plus 0. Right? So our answer is negative 54 over 20, or negative 27 over 10, or negative 2.7, whichever you want. Okay? So that is our slope at this point in this direction. Got it? Okay? So a little bit more useful than just the actual gradient, but still not as useful as what you're about ready to learn. So this would be the most important part of this section so far. Okay? So, yes. Okay. So, in order to really understand what's cool about the gradient, if the gradient is capable of having some level of coolness, maybe it's not. So maybe that's not a true statement at all. But in order to understand what the gradient is telling us, you need to remember this little fact about dot products. Okay? Got it? So, let's say, okay, so just keep this fact in your mind. Now we're going to go a different direction real quick. So, let's say we had some function, f of x comma y, so some function of z, okay, where that function mapped out a mountain. And we were on that mountain. And we wanted to climb the mountain in the fastest possible route. So in order to achieve that goal, we would have to take the steepest possible route to get to the top of the mountain. And if we could instantaneously always do the steepest choice, that would be our quickest way to get to the top of the mountain. Does that kind of make sense? So we're trying to figure out at any given point, x comma y, what direction, so at any given point x, y, which directional derivative is greatest? That's the question we're trying to answer. Okay? So somebody that was way smarter than me, but only relatively older than me, because I think this has only been known for like the last 200 years, okay, was like, well, let's just start by examining the directional derivative. So, they said let's just start by examining the gradient. So the gradient is f sub x of x comma y I plus f sub y of x comma y j. And they're like, well, that doesn't really do anything for me. Okay? So they were like, okay, it's equal to so they were like, okay, let's think about what the gradient would be. I'm sorry, the directional derivative. Okay, so they're like, well, the directional derivative is the gradient, okay, dot a unit vector. They're like, okay, so if I wanted to maximize this, okay, what has to be true about these two things? Well, smart person was like, well, let's remember this. Okay, so let's write the directional derivative I have no idea what that one's for. Let's write the directional derivative as the magnitude of del f times the magnitude of u times the cosine of theta, okay, where theta, if you remember this, is the angle between these two vectors. Okay? Got it? Well, they were like, what maximizes this function? What's going to maximize the slope of the line what's going to maximize the slope of the line in any given direction? That's what we're finding. We're trying to find the steepest step we could take from this point. Well, that's going to be when theta is 0. Okay, and that just means that we want our unit vector and our gradient to be in the exact same plane. And that's what the gradient does. It's when we find it, it is already in the same plane. So, as it ends up, what happens is, the answer to this little question is just the gradient. Meaning, if we find the gradient of any function, and we pop in any single point on a surface into the gradient, the resultant vector points us, because of this fact, it points us to the direction of greatest increase. And if you can think about like a heat-seeking particle, like a heat-seeking missile, that's exactly what it's doing. It's constantly changing its path in order to find the hottest instantaneous next point. Okay? So I told you at the beginning of this that hopefully this would make more sense at the end. So if you remember what we did here, we found the gradient at a point that was on our curve. Remember, this was actually the point 1, 2, 4. You remember that? Okay? And we found that to be the vector 6, 4. Are you still with me? I'm almost done. So here's what this means. If you were standing on this mountain at this point, at what point? At the point 1, 2, 4, right? And you were just curious. You were like, which step, which direction would I take in order to maximize my increase in change? This would be the step. But keep in mind, a vector has no position, so you're really imagining that step taking place right here. I told you this graph was not the graph of this, because I couldn't graph it. You remember that? So, at the point 1, 2, 4, the direction of greatest increase or greatest change is the direction 6, 4, or the direction 3, 2, or the direction 1.5, 1. You could also make it a unit vector. It doesn't matter. It's all pointing to the same direction. Does that make sense? And I hope that you could, at least out of curiosity, envision how this would affect a profit equation. If you're at a current point in time and you're making something, and that something involves more than one variable, and you want to know what direction should I go next to maximize my profits, you could find that out using math. That's it. That's all we're trying to teach you here. Got it? And then just a little bit of like a next step. So, fun fact. Here, I'll do this for my third bell because they like it when this happens. Have you ever seen this feature? The gradient, and I don't know how to spell it, points toward the step of maximum instantaneous. Uh-oh. Oh no. Uh-oh. This is not going to go well. Increase. This is why I don't do this in general. Oh! Oh, it did it. Excellent. I thought instantaneous was going to be messed up. Okay? Now, you already knew that. I explained that to you. Minus del F. Let's see what this does. PF. Not good. Okay? What does minus del of F point to then? Think about it. It's instantaneous. What did you say? What did you say? Minimum okay. That's how the book puts it. I like Sabrina's way better because the minimum increase is the maximum decrease according to the book, but I think there's some semantics involved there that's kind of weird. Okay? But what it's telling you is, if we go back to our mountain climber example, if you're on the mountain, see, this is a bad example. I don't want to, because it's not the actual curve. Okay, well, we'll just draw another mountain. Okay, if you're on a mountain, and below you is the shadow of where you actually are, and if this vector, well, that wouldn't be that vector. Let me try to get it right. If that vector represents the direction of maximum increase, it's telling you that the slope of this green line is the highest possible slope in any direction that you step. Does that make sense? Well, what that means is that if you were to step in the opposite direction, so if this is minus del of F, then that is going to be your steepest instantaneous drop. The maximum instantaneous decrease, yes. I agree, but if you read the way the book writes it, it says it's the minimum instantaneous increase. So they're assuming that the minimum increase is the same as the maximum decrease, and I totally disagree. So think about this. Your green line is represented as del F. That is your path to the top at any instantaneous point. I want you to know it is not pointing you towards the top of the mountain. It's taking you to the next step that will get you up the fastest. So like as you're going, this is going to keep changing, you know? It's not going to be a direct route. Does that make sense? This pink line represents the most dangerous step you could take. The slipperiest or greatest change in the negative direction. Does that make sense? Such a good question, Ted. So, at the top of the mountain, what happens? At the top of the mountain, there will be the result for the gradient will be 0 in all directions, and then we're going to find that that is what's going to be called a critical point, and that's exactly where we're going in this class next. Okay? So that is not this chapter, but that's the right question to ask now that you understand what the gradient is. Got it? Hey, Caroline, can I get a boom? Thank you. Boom.